Hi, how's everyone? Ran through Tut questions for week 7 today. Let's jump straight into it. We've got question 1. We've got bicycle sells an average of K. Sells an average of K bicycles per day from their store. A large number of days was sampled and at least one bicycle was sold in 98% of the days. So we know the probability of X being greater or equal to 1 is equal to 0.98. And so how are we gonna find out what K is? That's what the question asks. So we estimate K, the number of bicycles sold per day. So they've given us the probability that X is greater than 1. So they sell 1 to infinity bicycles on 98% of the days. How are we going to figure out what K is with this? In practice, or probably not in practice, you could find out what K is if you work this out for infinity. But why don't we think about it the other way? So if we've got X is greater than 1, or if we have less than 1. So what's the probability of X being equal to 0? That's just 1 minus that. So 1 minus 0.98. That's equal to 0.02. So we now know that for exactly 0 bicycles being sold, the probability associated with that is just 2%. So that can really help us out. So we're going to pop this straight into our Poisson to find out what K is, because K's are unknown. K is equal to question mark. This is a Poisson distribution because we're counting how many bicycles are sold every day. And so we're just going to pop it straight into our formula. So we've got e to the negative k, because k is our average, times k, the average to the power of 0, because it's 0 bikes, over 0. And that is equal to 0.02. And so essentially that becomes 1, that becomes 1. We end up with e to the negative k is equal to 0.02. How do we get to k? We ln both sides. So we have ln e to the negative k, 0.02. Remember the k can come out, so we end up with negative k is equal, negative k ln e is equal to ln 0.02. So in essence, it's negative k is equal to ln 0.02, k is equal to the negative ln 0.02, k is equal to, now I pop this into our calculator, negative ln 0.02, k is equal to 3.912. So that is the average. That's the average number of bicycles sold every day. Cool, we have our average now. So, question B goes, what is the probability that in 3 days only 5 bicycles are sold? So we have an X value, they want to know exactly 5, but we have 3 days. Our lambda, or average, lambda is equal to the average K, is 3.91 per day. So we have to somehow get that into a 3-day average. How do we do that? We just multiply by 3. So 3.912 times 3 is equal to, excuse me, 11.736. So there we go. Do you have any? Yep, okay. So that is our new average. That is the lambda per 3 days. Question B, remember. And we need to find now that 5 bicycles result. So we end up having e to the negative 11.736 times 11.736 to the power of 5 over 5 factorial. Nice and easy, and we pop that straight into our calculator. So we're going to have e to the negative 11.736 and then times by 11.736 to the power of 5. And we're going to divide that by 5 factorial. And we end up with 0.015 with a bit of rounding. Awesome. Okay, so there you go. That is the probability of selling exactly 5 bicycles in 3 days. Nice and sorted, plus some distribution. Cool. We now move on to question 2. We have question 2. A certain ice cream seller at a sports event sells ice cream at an average rate of 1 per 30 seconds. So we have lambda is equal to 1 per 30 seconds. Very important, this per what time unit. So if it was per minute, it would be equal to 2 per minute. What is the probability that the ice cream seller sells 10 ice creams in 3 minutes? Okay, so we now have to adjust our lambda into 3 minutes. So we have it for 30 seconds, and per minute we just multiply it by 3. So lambda is equal to 6 per 3 minutes. Nice and easy. We have our lambda, we have what we want to find out, sells exactly 10 ice creams. We're counting number of events happening in how many ice creams are being sold, so we're going to have a Poisson distribution, so we just use our formula again. So e to the negative 6 times, we have 6 to the power of 10, power of 10 times 10 factorial, and that is equal to, e to the power of negative 6, I'm going to use brackets, e to the negative 6 times 6 to the power of 10 divided by 10 factorial. Sorry, I forgot the divide sign. Divided by 10 factorial. There you go. We end up with 0.041. 0.041. Happy? Yep, I think we are. So there we go. Question A. Okay. B. If an ice cream has just been sold. Okay, that's some key information there. An ice cream has just been sold. What is the probability it will be at least 10 seconds before the next ice cream is sold? Okay, so you've been given an ice cream that's just sold. What is the probability it will be at least 10 seconds before the next ice cream is sold? So, key information, ice cream just been sold, and it'll be at least another 10 seconds before the next ice cream is sold. And so, we're looking at from 10 to infinity in essence, because we want more than at least 10 seconds, so 11, 12, 13 kind of thing. What I'd recommend is that we adjust our lambda now to per second. Remember, our lambda is per 3 minutes. So how do we get to 10 seconds? Well, we can jump back to see what it was per 30 seconds. Just divide that by 3 to get it per 10 seconds. Or maybe let's do it per second. So just divide it by 30. So we have lambda is equal to 1 over 30. So 1 over 30 ice creams per second, per 1 second. So what we're going to be doing, we're going to be using the exponential because we're looking at time between ice creams being sold. We've got 10 seconds all the way to infinity. We're going to have 1 over 30 e negative x over 30. Happy with that? I think we are. Negative 1 over 30 dx. Practice, practice, practice. You'll find out that this works out to negative e to the negative x over 30. 10 and infinity. The infinity pops in, becomes 0 because anything over an infinite number is 0, so we end up with 0 minus e to the negative 10 over 30, plus, because the negatives, they cancel out and become positive. And so we can pop that into our calculator. There's 1 over 3 as well, so this is just equal to e to the negative 1 over 3. We can do this, so we have e to the power of negative 1 over 3. And that is equal to 0.717. There you go. So that's the probability that will be at least another 10 seconds before an ice cream will be sold. Okay, awesome. Happy with that question, dude. Done and dusted. We're now going to move on to question 3. So we have question 3. The duration in minutes of a radio broadcast on a certain radio station is approximately exponential distributed with a lambda of 1 over 5. Okay, so that's quite nice. So they've been given us the lambda 1 over 5. We know it's exponential. That helps. 3 broadcasts. What is the probability that no more than 2 will last for 10 minutes or more? So now how are we going to approach this? So this is probably the most complicated part of the question, is just finding out what the rate is. They've given us the lambda, it's just 1 over 5. They haven't said 1 over 5 per hour, 1 over 5 per 5 minutes, or whatever. But they say the duration in minutes of a radio news broadcast is approximately with lambda, so we're going to assume this is per minute. So 1 over 5 per 1 minute. We've now been given a time of 10 minutes. We can leave it 1 over 5, we can adjust it. Maybe for the sake of this question, what I'll do is I will adjust the lambda So we can see how things change, see how things changed, and we use a different lambda. Okay, so we've got lambda per minute, that's 1 over 5. We're going to go per 10 minutes, that's equal to 1 over 5 times 10. So 1 divided by 5 times 10, that's just 2. So we have a lambda of 2 per 10 minutes. And remember, we want to find out the probability of it being greater than. Because our lambda is now in 10 minutes, our integration numbers will also be in 10 minutes. So if we have integral from 1 to 5, that is essentially from 10 minutes to 15 minutes, not 1 minute to 5 minutes. It all depends on what you've set your lambda into. So quite important there. We want to know the probability of being greater than 10 minutes, and so in essence, what we're going to do is we're going to integrate from 10 minutes to infinity minutes. Remember, as lambda is in 10 minutes, so that becomes 1 being equal to 10 minutes, all the way to infinity, because infinity, it doesn't matter what you multiply it by, it's still infinity. So we have 2e to the negative 2x dx, because remember our lambda is now 2. From a bit of working out, we find out that is equal to negative 2x for 1 and infinity, and that essentially just works out to be e to the negative 2. 1 fits in there. So what do we end up with? We end up with e to the negative 2. Negative 2. End up with 0.135. Are we happy with that? I think we are. So there you go. There's the probability of it being more than 10 minutes. For one, of course, sorry. I forgot to mention this is for one broadcast because we have to find out the probability out of 3 broadcasts. We're going to do this for the other 3. What other distributions can we use? If we know an average, we know the probabilities of going over a time limit. We're going to be using the binomial distribution. So we have the probability of it being greater than, also the probability of being less than. It's just 1 minus that. 2 outcomes, it can either be more than, it can either be less than. Go use binomial for 3. And so in essence, the question goes, I have 3 broadcasts, so we have 3. What is the probability that not more than 2 will last for 10 minutes or more? So in essence, they want 0 broadcasts, 1 broadcast, and 2 broadcasts. We're going to think about the opposite way. We're going to think about all broadcasts, and then we just go 1 minus that, so we're going to do 3 choose 3. So binomial, we have the probability of it being greater than, so it's going to be 0.135 to the power of 3 times whatever 1 minus 0.135 is to the power of 0. That just becomes 1. So we don't even have to bother with that. We can pop this into our calculators. We have 3 choose 3 times 0.135 cubed. That is equal to a very small number of 0.0025. Now remember, we're going to have to do 1 minus this. So this becomes 1 minus 0.0025. 1 minus 0.0025 is equal to 0.9975. There you go. So 2-part question. Sorry, I didn't make it clear exactly what we were doing. First part of the question, we had to look at the probability of it being more than 10 minutes. Next part of the question, we had to look out for 3 broadcasts. Was the probability that less than or equal to 2 go over 5 minutes? 10 minutes. So yeah, two parts to that question. Question B, what is the probability that a broadcast will last at least another 2 minutes, given that it has already lasted 5 minutes? So, quite interesting how to deal with this question, because I think if you recall, you'll remember that one of the key bits of information about the exponential distribution is that the probability, and the Poisson, of course, the probability of an event occurring is independent of the time that has already elapsed. So it doesn't matter how long you've waited to sell your ice cream, for instance, it doesn't matter how long you've already waited. It matters how long you're going to be waiting from the time that you test. So the piece of information where they say you've already, that the radio news broadcast has already lasted 5 minutes, doesn't really matter, because it's independent of that. So in essence, what we're going to be doing, last at least another 2 minutes, so 2 to infinity. We have our lambda. We had it per minute, 1/5 per minute. We're going to leave it at that. So we're going to have lambda from 2 to infinity, 1/5 e to the negative x over 5 dx. Work out negative e to the negative 5 over x to infinity. That's just equal to e to the negative 2/5. And that is equal to e to the negative 2/5, 0.67. There you go. And there, that's our probability. So that's question 3. Done and dusted. Key information of independent, doesn't matter how long you've already waited. So don't worry too much about that. Okay, cool. So question 4. We have question 4. We have potholes occur in a particular bad stretch of Eastern Cape Highway at an average rate of 4.4 potholes per kilometer of highway. So we have an average, so we could say a lambda. Lambda is equal to 4.4 per 1 kilometer. What was the probability of one pothole in 100 meters of highway? So now we're counting probabilities not counting probabilities, we're counting events. We want to know the probability of one pothole in 100 meters of highway. What distribution are we going to use? We're going to be using the Poisson distribution because it looks at counting events. We're going to have to adjust our lambda because our lambda is in kilometers. We're going to have to get per 100 meters. So lambda is equal to 0.44 per 100 meters. Do this in your head, just that divided by 10. So kilometers, 1,000 meters. So nice and easy. We're gonna have our Poisson distribution, e to the negative 0.44 times 0.44 to the power of 1, because it's one pothole, over 1 factorial. We pop that into our calculator. Negative 0.44 times 0.44 is equal to 0.283. Nice and easy. Question 1 done. So that's the probability of one pothole being exactly one pothole. Cool. Question B, the probability of more than 3 potholes in 250 meters of highway. Oh, this is going to get a bit tedious. Okay, so let's set up our lambda so long. Lambda is equal to that divided by 4. I think that just becomes 1.1. Yeah, 1.1. 1.1 per 250 meters of road. Because remember, divide by 4. Kilometer divided by 4 is 250 meters. We've got our average per 250 meters. The question goes more than 3 potholes. We're going to have to be using the binomial again, and we're going to do it for 0, 1, and 2, and we're going to do 1 minus that, because if we did more than 3 potholes, 3 as well, more than 3 potholes, we're doing 4 all the way up to infinity, and that's a bit of a nuisance. Okay, so set this out. We're going to have e to the negative 1.1 times negative 1.1 times 1.1 to the power of 0 over 0. Just works out to that. Plus e to the negative 1.1 times 1.1 to the power of 1 over 1 factorial. Plus e to the negative 1.1 times 1.1 squared over 2 factorial, plus e to the negative 1.1 times 1.1 to the power of 3 over 3 factorial. Okay, awesome. And that is equal to, nice and easy, that becomes 1, so we just have e to the power of negative 1.1. So we have 0.333. Now we're going to do a bit of rounding. Plus, the same thing, but this time we have times 1.1 to the power of 1 divided by 1, that stays fine. 0.366 plus the same thing but now squared and divided by 2 factorial 0.201 and then 3 factorial into the power of, dang it, okay, so we have to do this from scratch. E to the negative 1.1 times 1.1 cubed divided by 3 factorial, and we end up with plus 0.074. Okay, leave that out. Okay, so we need to sum all those together, so 0.333 plus 0.366 plus 0.201 plus 0.074 is equal to 0.974. And we're doing 1 minus, so 1 minus 0.974 is equal to 0.026, I believe. Yep, I think that is right. Yep, checks out. If you left the rounding and you still would have gotten the exact same number, but there you go, 1 minus, we have our probability. Awesome. Cool. Now going on to question C. Now this is a bit of an interesting question because we're looking at the distance between events. Now previously in your exponential distribution you would have only worked with time between events. But the same can be for distance. You know, you could also, if you wanted to, you could measure in number of ice creams. So like how many ice creams or how many cars in between 2 roads kind of thing. You know, it doesn't really matter what your time or measurement unit is as long as it's something you can measure and something that can increase and decrease. So for our sake, we're going to be looking at meters here, 500 meters. So what is the probability that the distance between potholes exceeds 500 meters? So you could also think about this question in terms of you've just passed a pothole. What is the probability that it will be at least 500 meters until you hit your next? So what does that sound like? That sounds like an exponential distribution to me. So we're going to be using the exponential distribution. Remember, our mean is in kilometers, or our lambda is per kilometer. We can maybe set this up in per meter, so we divide that by 1,000. So 4.4 divided by 1,000 is equal to 0.0044 per 1 meter. And so what we're going to do, we're going to integrate from 500 to infinity of 0.0044 e to the negative 0.0044x dx. Work that out, that just becomes negative e to the negative 0.0044x for 500 and infinity, which then becomes e to the negative 0.0044 times 500. And that is equal to, we have e to the negative 0.0044. Oops, you're going to have to also use by 500. It's equal to 0.111. That's a bit of rounding. Awesome. There you go, nice and set out. Exponential distribution. C, done. Now we look at D. So the contractor is sent out to investigate and fix the potholes on the highway. He decides to first do some testing of his own on a number of potholes found in the highway. He randomly selects and marks out on a map 10 200 meter stretches. So he's got 10 200 meter stretches he's going to be looking at, and then goes to count the number of potholes in each of these stretches. What is the probability that 8 or more of the random chosen stretches of highway are free of potholes? So how are we going to think about this question? So if we have, let's think about it in terms of the one of the 200 meter stretches. Remember, he's got 10 of these. Right, this is going to be also a two-part question like we'd seen previously. So we have 200 meters of road. We're going to look at trying to find out what the probability is of one of these having no potholes. Because remember that he's counting, or he wants to find out the probability of a random chosen stretch having no potholes. So if we're counting the number of potholes per a certain stretch, what kind of distribution can we use? We can use the Poisson distribution. So we've got our lambda is in kilometers, so for per 1 kilometer. Let's set this up in per 200 meters. So we divide this by 5. Yep, 4.4 divided by 5 becomes 0.88 per 200 meters. Okay, so there we go. We've got our new lambda. So we're gonna now essentially excuse me, negative 0.88 do the Poisson. We've got 0.88 to the power of 0 over 0 to negative 0.88, and that is equal to second negative 0.88. 0.415. 0.415. Okay, cool. So we've now found the probability that in one of these 200 meter stretches, there'd be no potholes. So this is the probability that you won't have any potholes in one of these 200 meter stretches. The question then speaks about what is the probability that 8 or more of the random chosen stretches of highway are free of potholes. A bit of a tongue twisting going on. And so how are we going to do this? So if we know the probability of there being no potholes, and we can find out the probability of there being at least one pothole, and we want to know the probability of how many of these 200 meter stretches actually don't have potholes, or if we want greater than 8, we can use the binomial distribution. And because it's going 8 or more, we're going to have 8, we're going to have 9, and we're going to have 10. So in essence, we're going to have 10 choose 8 times 0.415 to the power of 8 times, this is where it comes in, we're going to have 1 minus 0.415, 0.585 to the power of 2 plus 10 choose 9, 0.415 to the power of 9, 0.585 to the power of 1 plus 10 choose 10, 0.415 to the power of 10, 0.585 to the power of 0, that just becomes 1. And we use our calculator to find out what that is equal to. So we have 10 choose 8 times 0.415 to the power of 8, yep, times 0.585 to the power of 2 plus 10 choose 9 times 0.415 to the power of 9 times 0.585 plus 10 choose 10 times 0.15 to the power of 10, and there we go, and we end up with 0.025. I think, are we happy with that? I think I may have made a bit of a boo-boo. Let's have a look. To the power of 8. Oh, there you go. Let's have a look. Power of 2. Yeah, there you go. Okay. Sorry about that. Bit of a typo in the calculator. Always good to double check that you've done everything correctly. Works out to be 0.016 rounding. Nice and easy. Okay, so that is the probability that at least 8 of these 200 meter stretches are free of potholes. So a two-part question like we've previously seen. Okay, we're now going to focus on question 5. Question 5 deals with the normal distribution. Okay, so we have excuse me, a small team of bricklayers is building a warehouse in Cape Town. The number of square meters they complete every day depends on many factors and can be approximated by a normal distribution with mean 13 and standard deviation of 12. Okay, so we know x follows normal with 13 and 2 squared. Mean variance The progress for each day is independent of all other days. Okay, important. If they work on the warehouse for 15 consecutive days, what is the probability that they will build at least 200 square meters of brickwork in this time? Okay, so we have 15. We have at least 200 meters. So now we're going to set up, we've got the distribution for 1 day. This is for 1 day. We need the distribution for 15 days. Because they're independent, we can essentially add them all up. So if that's for x1, we could have, let's say, let's call this y. So y is the distribution of 15 days. Y is equal to x1 plus x2 plus x3 all the way down to plus x15. Now because they're independent, we essentially can just add the means and standard deviations. In essence, multiply them. But be careful, remember we're adding, we're not multiplying. If we are multiplying y by 15, the variance would have to be multiplied by the square of that number. But because they're independent, we're adding them. So y becomes normal of 15 times 13 and 15 times 2 squared, or 4. Which is equal to, let's have a look, 15 times 13, 195, and 15 times 4, 60. Awesome. Okay, so now what are we going to do? We want to know the probability that they will build at least 200 square meters of brickwork in this time. Okay, so at least we want greater than, and so we're going to do our z. Z is equal to x bar minus mu over sigma, which is equal to 200, because that's what we're testing. 200 minus 195 over root 60, that is equal to 5 over root 60, which is equal to 5 by root 60, 0.645. Awesome, so we now have the z value. We're going to look it up in the tables on the back of intro stats. Practice, practice, practice. We're going to be looking up 0.65, so we're going to round 2 decimal places. 0.65, 0.65, we end up with 0.2422. 2422. And so, is equal to, so P of Z is 0.2422. But because we're looking for greater than, if you draw your standard normal table, we found this value of 0.645. This value over here is equal to 0.422. We want greater than. We want this half. So how do we get there? Remember, this half is equal to 0.5, and this half is equal to 0.5. So to find that, we essentially just have 0.5 minus 0.2422. And that is equal to 0.2578. And there you go. So we've 0.5 minus that value gives us our p-value over there.